Okay, so I'm super excited to have Jon Kleinberg here to speak to us. Jon is one of the leaders in networks and algorithms. He's one of the most original people thinking about everything from email to social media. And today he will talk to us about the upcoming topic of LLMs.
All right, thanks very much. Yeah, thanks for the invitation to come speak here. So I wanted to talk a little about some work that we've been doing trying to think about large language models. Now, obviously that's a topic on many people's minds, and there's a lot of different ways to go about this. This grew out of some discussions that I've been having over several years with my longtime co-author, Senthil, who's a behavioral economist now at MIT. And then at the end, if I have time, I'll get into a little bit of more recent work building on these models that I've been doing with Fan Wei in the Duke Math Department, who was if I have the chronology right, was a postdoc here in 2019 and 2020. There's been some, very interesting work that based on some insights she had about this model that I'll be telling you about. Okay, so large language models. There's like a lot of ways you can think about this. Like, there's so much going on right now. The question is, how do you contribute if you're trying to think about things sort of mathematically or conceptually? And so, I mean, just to draw sort of a picture, like one way we sort of began looking for problems in this space is to sort of think about a picture that computer scientists often like to draw, which is the hourglass of abstractions, right? In some sense, like, this picture of the hourglass, I think, grew out of originally the idea that, like, your computer has a chip in it, and there are chip designers who know how to build chips. And then there are programming languages, and the people who write in the programming language don't necessarily have to know how the chip works. People who build the chip don't necessarily have to know how the programming language was implemented. They sort of meet in the middle at this thin part of the hourglass, right? And, we see this in the everyday technological world also, right? The fact that you can drive a car without knowing how a car engine works is because in the middle we just have a steering wheel, a brake pedal, and a gas pedal, and that's the functionality that the car exports. You could argue that with large language models, something similar is happening, that we're getting this genuinely new functionality called language generation, right? The ability to just generate fluent text. And we're trying to think how that can be put to use. And when we think about that, we can ask theoretical questions both above and below the thin part of the hourglass, right? Below, which I'm not going to be talking about today, is questions about, say, the transformer architecture. What's its computational power? What can it compute? How do we train it? How well does it generalize, right? All the things that are down to the level of the actual circuitry of the deep neural net that's doing this. And then above, which is where I'm going to try to sit today, is this question of, what can you build once you have the ability to generate fluent text? And sitting in the middle is this kind of, like, I would say thus far unmodeled question about, like, how should we talk about language generation just as an activity? Like, what is that functionality that we've just been given, right? And there's a lot of value in doing this, right? In the same way that, cryptography, you can talk about how do we implement cryptography, what do we build in cryptography? And in the middle is this metaphorical story of Alice and Bob communicating across a wire while someone listens in, right? And it's, of course, been amazing how much mileage over half a century you can get out of the metaphorical story of Alice and Bob communicating over a wire. We don't have that story for large language models, right? Who are Alice and Bob in the large language model? And so part of this talk is going to be an attempt to try to find Alice and Bob in the middle of this picture. Like, who are they if we're talking about large language models? Okay, so it's sort of a cliche when talking about large language models, when you give talks about them, which is to sort of bring the model in as a character in the story at some point. So I'll just briefly indulge in this cliche. We could, of course, ask ChatGPT what problem it thinks it's solving. And it gives you, of course, a very thoughtful answer. It likes bullet points. It always hedges compulsively. But, I'd say kind of here is where it kind of gets to the punchline, that the primary objective is to learn a processing model of language that can predict the likelihood of a sequence of words or tokens in any context. Right? That's kind of what a large language model is doing. It's putting a probability distribution over utterances, and then it's trying to select out the most likely utterances. Okay, let's start with that. And in some sense, where my co-author Senthil and I started was that this is certainly the received wisdom on what they're doing. Let's just paraphrase it here. Let's find them all, assigns a conditional probability to every possible sequence of words, and then we're just going to, like, say the likely ones, right? So the large language model decided that this long piece of text, which continues for quite a while, had high probability in the space of all pieces of text you could say in response to that question. But we actually wanted to back up because, again, we're trying to find the simplest model we can. And while this is simple, let's ask about, like, there are certain things that it's not going to need to be there. For example, the idea that there's probability here, right? The idea that the large language model is about putting a distribution on things was sort of our choice to put the probability here, right? That was our modeling decision. It's not that probability necessarily is inevitable when you talk about language modeling, because after all, if I wanted to state the problem even more simply, I could say, I would like to simply design an algorithm that observes strings from an unknown language, and after a while, eventually begins producing valid strings that have never been seen before. And that's sort of the magic of language models, that they see things come in, and eventually they just start speaking in ways that sound fluid. So this version sounds too general to be useful. Like if I just say this, it feels like, well, that's too general. But let's at least sort of sit with this problem for a little bit and just see how far we get with it. Okay, so in this completely abstract formulation, again, the goal is to utter strings. A string is a sequence of symbols from a fixed alphabet. So it's kind of like classical language theory, right? And a language is a set, right? So alphabet, finite length strings, and the language is a subset of those strings. I think probably, the motivation here comes from, I'd say actually probably the symbols are actually like the words of English, say 50,000 words of English. The strings over those symbols are like paragraphs of English. And the language is all valid paragraphs, let's say. Like that's probably the motivation. If you want something that's fully precise, because of course, what is a valid English sentence? We could disagree on that. A fully precise version would say strings are ASCII characters and the language is all strings that are well-formed C programs or Python programs. And that's certainly a fully well-defined question. Right? You can ask, could I build an algorithm that just watches C programs pass in front of me and after some finite time just outputs valid C programs? All right, that's the question. So it's a little too general to be true, but then you should be able to do this. And one reason why it feels a little too general is that we've seen a model like this before. There's a 60-year-old model due to Mark Gold, 1967, which was in the end sort of fully characterized by Dana Anglin in 1979, that imagines language learning as a game played between an adversary and an algorithm. Okay, and this is going to be kind of like the Alice and Bob and Our Story, 2 players. Okay, and here's how it works. So the adversary thinks of a secret language that is known to be produced by some representation, some finite representation. And the representation could be a kind of tree grammar, finite automaton, some space-bound Turing machine, whatever it is you want. In fact, actually, I don't really care about the representations. Let's just imagine it says, I'm thinking of a countable list of possible languages, L1, L2, L3, all of them infinite. And my secret language K is one of them, and I won't tell you which one. Now, what does it mean I specify this family of languages for you? Well, you and I have a black box sitting between us, and you can query membership in the language. So in one step, you can ask, here's a string W, here's an index I, is W belonging to L? Okay, and that's how we show language. But if you want everything I'm saying, you could just think this is all the context-free languages if you want. Either way is fine. Okay, but it's much more general than that. And we'll think the languages are infinite because whatever problem we're trying to solve, language generation or whatever, the problem is never that we're going to run out of things to say. So we might as well assume that it's infinite. Okay, so here's the game. This is Mark Gold's game from 1967. The adversary enumerates the strings of K one by one, right? It allows repetition if you want, but every string of K must occur at some point, right? It's enumerating. And in each step, the algorithm is trying to guess the identity of the language. So it guesses an index, I sub t, with the goal that L sub I sub t should eventually be the true language. And so it's watching, trying to guess what the language is. And the algorithm wins if there's some finite step t star, after which it's correct forever. Now, K might occur multiple times in this list, so the index could jump around as long as it's always K, as long as the language is always correct. Okay? All right, that's what it means for the algorithm to win. That has identified K in the limit. Now, Mark Gold was writing this paper in 1967. There wasn't a lot of big data sets. There weren't a lot of powerful computers. He was only partly thinking about computation. He was also in part motivated actually by infinite language learning. Because the question is, imagine a 9-month-old that is listening to language. They listen to their parents talking around the house. They've heard by that point a few 100,000 words of language in their native language, spoken at home. But they're trying to learn the language under some severe constraints. One is, yes, the parents sometimes make grammatical stumbles, but fundamentally people don't speak in gibberish for long periods of time. So the infant is only seeing effectively positive examples. Second, the 9-month-old can't verbalize, right? One of the amazing things about infant language learning is the baby gets pretty good at language, never having actually spoken to anybody. So the algorithm, the infant, is never told, it's guessing. I think the index is like index 100. I think it's 1,000, whatever. It's never told if its guess is correct because it can't verbalize. It can't ask, is my guess correct? Right. The 2-year-old can, but the 6-month-old, it's very hard. And it also can't ask membership in the language. It can't say, is this a valid string? And so the question is like, once the infant becomes a toddler who can even babble, then the game changes a little bit. You can start asking things. But there's a phase where it's literally just receiving. And it gets pretty far. Okay, so this feels kind of impossible. And that's because it is impossible. So Gold's theorem, 1967, says there is no algorithm that can achieve language generation, language identification in the limit, even for very simple collections, such as, say, all regular languages. Regular languages are much too hard for this problem. Even just really simple periodic language, much too hard. And Gold and Angluin came along 10, 12 years later and actually characterized exactly the collections for which algorithm can perform identification in the limit. And kind of the most interesting category is sort of, let's call them pattern expansion languages. So all strings of the form 0x, 1y1, anything for x, anything for y. That's kind of the most interesting family where you can actually do this. But you gave an if and only if characterization. Okay, so that's fine. It was too hard. I mean, it was this completely worst case model in which I had this countable list of possibilities. I just say some strings and in finite time, I'm supposed to resolve which one it was. Not possible. And as a result, people said, okay, well, this was part of the motivation for the field early on turning to probabilistic assumptions. There were lots of other reasons, such as the fact that language really does have this rich statistical structure. So Sendel and I were talking about this. Sendel was pushing me like, why can't we just do something very simple? I remember this theorem. Grad school, I'm like, well, this is sort of why. But we realized something. This isn't actually the question we were asking. We weren't asking that the algorithm identify them. It doesn't have to ever know what the language was. It just has to generate from the language. This is not a minor distinction, right? The 6-month-old who picks up language and becomes a 1.5-year-old who sort of babbles in the language and eventually becomes a 5-year-old who's fairly fluent in their native language. At age 5, they can't necessarily litigate boundary cases of English grammar. Right? If you quiz them on like, is this a valid, they can generate. Right? They generate by staying in some safe region in the language and not really exploring the periphery. In the same way that, a 30-year-old also can't always litigate edge cases of English grammar, right? That's hard. In the same way that with like, if the goal is to generate C programs, you can write C programs, but if you go to a super intensive coding interview where they show you something that does some bizarre null pointer dereference and say, would this compile? You might not get the answer right. Right? Identifying the language is arguably harder than generating the language. So we go back. We say, all right, let's try a new game. The new game is about generation. So similar setup. Adversary thinks of a secret language K, known to be one of this countable list. Adversary enumerates the strings one by one. One extra piece of notation now. S sub T is the strings you've seen from K up to step T. So it's some finite set of T strings. Okay. But now the algorithm has a new goal. In step T, the algorithm should output a string A sub T that should be new and valid, right? So it should come from K, but not from ST. It should say something genuinely new. And again, as before, all of the constraints that 6-month-old infants have, no negative examples, no feedback on if you're right or wrong. Okay. And now the algorithm wins, again, if there's some finite step after which it's correct forever. From then on, every string it generates, A sub T, comes from K minus ST. And then we'll say it is generated from K in the limit. All right, so questions about that? That's the question. We would like to design, if possible, an algorithm that can generate in the limit. And we're hoping this problem might be more tractable than identification in the limit, which is impossible in all but the most simple cases. And so Sendel and I thought to ourselves, we started asking around, and people had not really thought about this version of the question. So, okay, it's a well-defined question. We thought, what if we went back to Angluin's characterization? I mean, if I can identify in the limit, I can generate in the limit. Because I just take my current guess for the language, and the language is infinite. I've seen a finite number of strings from it. So I just start using my membership oracle. I start querying strings until I crash into one that's in the language that's new, and I upload it. So if I can certainly generate. So Angluin's characterization says I can certainly generate in those cases. We thought maybe we could revisit Angluin's characterization and characterize the language families where generation in the limit is possible. Is it a bigger one? Does it contain the regular languages? Like, what's going on? And the answer surprised us. This was our theorem, that there's an algorithm property that for any countable collection of languages, the algorithm can generate in the limit. Okay, so generation in the limit is possible no matter what the family of languages is. Okay, and so there's something just dramatically different about generation and identification. Now, I'll come back to like exactly, I mean, any really means any, right? Our model of computation is that we have a black box sitting between us that can answer membership queries. And that's all that we have. Like I just ask, is the string, is string 8 in language 5, and it just tells me, right? A gigantic two-dimensional countably infinite lookup table. And that's all we need. Now, there's a question of like, what do I mean by an algorithm? So one thing, and I'm going to mean this in two different senses. Gold's theorem, the fascination with Gold's theorem was never about actual computability. As in, there tended to not be a fixation on like, is this really computable by a Turing machine? Because the challenge is not really the computational resources spent by the algorithm. The challenge is it doesn't know what the secret language is. And so you can do non-computable things and still not be able to. So Gold's theorem applies even for things that are equipped with like powerful oracles for the halting problem and things like this. And so the result is actually cleaner if we have an algorithm that's equipped with an oracle that can solve actually subset containment among languages. So I'll do it first that way. But of course, we kind of wanted a real algorithm. And so in the end, I'll say how we break that down and actually have an algorithm. So I'll do it kind of in two steps. Of course, any algorithm that does this is going to have to sort of win without knowing how it won, because Gold's theorem says it's never going to know what the language was, even though it is going to generate in the limit. Right? So you're going to sum it up. Okay. And so what's the key point here? The key point is that the algorithm, as long as it generates from some infinite subset of the language, that's good enough, right? You just have to generate forever. And again, in the same way that like you're a competent C programmer because you know how to stick to the subset of C you understand, that's what it's going to do. In doing so, it actually, although this model is extremely abstract, it actually gets us something that's been led to a bunch of interesting discussions with people who build these kind of models for a living, which is this tension between two things that we'll call validity and breadth, right? Validity says you must only generate valid strings that are in the line. And breadth says you should generate many strings, right? Because we'd like your output to be rich. We'd like you to be an interesting chatbot to talk to. Okay, and so validity breadth trade-offs are something which the field has not really made much progress in formalizing, and some sort of the hope here is that this maybe starts giving us a language for doing this. Right, at the two extremes, at one extreme, failures of validity we often call hallucination. The model is hallucinating, it's saying things that are invalid. At the other extreme, we have something that generative AI people call mode collapse, right? That the longer I go, the more it sort of collapses down to this very small subset, and that's all that it's willing to say. It's valid, but just not very interesting. Okay. And so the way our algorithm is going to work, and you'll see in a few minutes, it's going to sort of keep shrinking what it's willing to say. It's going to do this kind of controlled version of mode collapse where it kind of shrinks down. And the subsequent work that Fan Wei and I have been thinking about tries to get this question of like, is this necessary? Is it possible to generate in a valid way with significantly more breadth than the original algorithm has? Okay, so let's plunge ahead here. I want to talk about the algorithm. At least the version which has access to some non-computable oracles, I can actually just tell you how it works and prove it's correct. And then I'll sketch some other things. Okay, so before I do that, there's one other theorem. So that's the first theorem. There's a second theorem that's interesting, which is, suppose I only have a finite collection of languages, which means I promise you that this language, my secret language, is produced by a finite automaton with the most k states, right? So let's have all k-state finite automata, some finite set. Well, so then actually, Angluin's characterization says there is an algorithm for identification in the limit. So this is a tractable case for identification. So you could ask, like, what more could we want? Well, one more thing we could want would be to give you an actual a priori bound on how many steps it will take to succeed. Right? I'd like to inspect my collection and say, I promise you that within 1 million steps, if you show me 1 million examples, I will succeed. For identification, this is not possible, right? Simple example, like let's say language L1 is all strings and language L2 is even length, all even length strings. And you promise me that after 1 million examples, you'll know the answer. So I show you 1 million even length strings and ask you to guess, right? And either you guess L2, in which case I show you an odd string and you're wrong, or you guess L1, which is clearly a bad idea because all I ever showed you was even length strings. So, okay, so identification you will identify, I mean, there's a way to identify the limit. You should just keep guessing L2 until you first see an odd string, and then you guess L1. And because the adversary is compelled to enumerate the whole language, they must eventually output an odd length string if their idea is L1. So I can do it, I just can't tell you when it'll happen. But for generation, you can actually. So for generation, a second theorem, in the case of a finite collection, I can look at the collection, give you an a priori bound T of C, such that the algorithm will always generate from the true language within that many steps. All right. I mean, here it's clear what you would do. Just generate even length strings forever. Like, you don't even need to see examples. In this case, if you generate even length strings forever, you must be correct, because one of them is a subset of the other. So this is not a particularly hard instance. Okay. All right. So let's. Okay. So the easiest way to get but I'll mainly focus on the first theorem. The easiest way to get to the first theorem is to actually try some things that don't work. And we'll try one thing that doesn't work, which is actually kind of a dead end. We'll try a second thing that doesn't work, which is actually gets us partway there, and then we'll see what happens. Part of this came about just because the theorem is so simple to state. It felt like this theorem is either going to be trivially true or there's a counterexample. Like, it's very hard to picture the theorem that looks like this. The answer is yes, but for non-trivial reasons. And what was sort of surprising to us was that, as far as we can tell, the answer is yes for non-trivial reasons. You know, in the end, reasons that I can explain to you in this talk, but not reasons that I can say in one paragraph. Okay, so let's try some things. Like, why does the one paragraph solution not work? So I think the one paragraph solution, if the answer is yes, you're like, well, the answer is gonna be yes for roughly this reason. So let's try some. Consider the following thing. First of all, strings are not so fun to work with in real time on slides in a talk. So let's replace our countable ground set with just integers. Right, so languages are now subsets of the integers. The integers are just the indices of strings. It doesn't really matter. So suppose that my language family is very simple, right? Simpler than the regular language. It consists of all infinite arithmetic progressions. Let's say doubly infinite and also one way anchored to the left going to the right. Okay, so, and I would like to, generate an element from this. Well, you'll notice that after the adversary enumerates any two elements of K, I can successfully generate from it, right? If you show me -3 and +3, then I don't need more examples. I generate 9, 15, 21, 27. I just keep going to the right. I know those are my language. Actually, this slide has enough to, like, Gold's theorem does have a one paragraph proof, and this slide's enough to show you. Like, imagine we have to identify in the limit, okay? And so I show you these two and I say, okay, yes. And you say, I don't know, it's all things that increment by 6 starting -3. And then I keep going to the right, 9, 15, 21, and your guess is being confirmed. And so I wait till you guess that. As soon as you guess that, I say, oh, also -9. Okay, and then I keep going to the right. At some point, if you want to be correct, you have to guess it's -9 to the right. It's anchored at -9, because otherwise you'll be wrong. The instant you say that, I say, oh, also -15. And I keep going. And of course, in the end, the correct answer is the doubly infinite arithmetic progression. But you've been wrong infinitely often in doing that, right? And that's the proof of Gold's theorem. That's really all that's going on. And that's why it applies to such simple language families. Yeah.
Is there a way to like prove a version of Gold's theorem that holds for more languages where you say like, okay, you don't have to be correct always after some time step, but maybe you have to be correct like 99 times out of 100?
Yeah, it's an interesting question. So actually, by the end, we've wondered about theorems like this. Like, you could say, for example, the density of errors you make is going to 0, for example. Yeah.
Well, not even going to 0.
Or just is small, yeah. I don't know if I don't know if exactly. Obviously, I can do this kind of like data-free enumeration where I guess 1, then 1, then 2, then 1, then 2, then 3, then 1, then 2, then 3, then 4. In that case, I'll be correct infinitely often because I say everything infinitely many times. So I want something, but I want to say constant. So
yeah, but maybe you like need to be correct 50%.
Yeah, so like I'll need some extra density. I'll need some positive density. Right? I do not. We've looked for this. Is there something where you say I have to be correct at positive density? I don't know. It relates to some, toward the end, it'll be easier to come back to this question and ask it. Yeah, I think the sort of can I be correct on a positive density of guesses is probably a good way to ask the question. And I don't know the answer to that. Okay, so but yeah, it's a very nice question. For generation, right, it was clear. It suggested, okay, maybe the point is that there's this useful kind of closure operation. If I can show you a finite set S, let's say the closure of S is just the intersection of all languages that contain it, right? So all valid languages, because obviously, if there's anything in the closure that's not an S, I can just say it. Because by definition, it's in everything that could possibly be consistent, right? The story to picture is like, this is sort of like convex hull of my finite set. I put down some, I say, different problem. I'm thinking of a secret convex set in the plane. What is it? I put down a finite set of points. You say, I have no idea. There's lots of convex sets through these points. I couldn't possibly guess. Like, okay, how about generation? Generate from the convex set thing. Well, sure. If you generate from inside the convex hull, I put down 2 points. You can generate forever from the interval between them, and you'll be correct. So maybe we have kind of something like that going on. Right? Maybe there's a lemma we could prove that like the closure minus the set is always non-empty once it's large enough. It turns out this actually does work for my theorem too, that I can put an a priori bound with a finite collection. Closure gets you there, and it is sort of a fairly short proof. But somehow this can't really work for the problem, for the infinite case, because of slightly simpler, slightly more complicated examples. Imagine I have a slightly more complicated example, which is all sets of the form P, where P is an infinite regression, union V, where V is any finite set. Right? So it's like I have the my regression, but then I kind of just drop in some finite elements. Also now for any finite set S, obviously the closure is just S, right? Obviously I'm learning, there's nothing I can guarantee is also adhering to this finite set, because maybe everything you've seen so far is just V, and V has now come to an end, and you haven't even seen the arithmetic regression yet. It hasn't even shown up yet. So there's nothing you can know to generate. So closure in some sense is actually a dead end. I don't really know how to get closure to work. In the finite case, actually, it's very useful, but in this case, I don't really know what to do. Despite this, of course, you can generate in the limit. How do you generate in the limit? Well, what I could do is I could always just take the 2 rightmost points and look at their difference and go that difference one more out and generate that. Okay. So just look at my big mess of points, take the last 2, look at the gap between them, continue that gap one more out. The point is, eventually, in this enumeration, the adversary is going to run out of the finite set. And so eventually they're going to be having to output from the infinite regression. And at some point they'll generate enumerate so long that the infinite regression contains the rightmost 2 points. And then I'm fine after that. But it feels like a very ad hoc solution tailored to just this example. And this is sort of like, as we were originally thinking about this problem, we would have one ad hoc solution after another. And the question is like, okay, so what's the general solution? So let's try something much more general that's not tailored to any one example. Okay, so attempt number 2, also wrong, but gets us much closer. Let's really use the fact that we have this countable list of languages, L1, L2, L3, and so forth. I'm just going to start with the hypothesis that the true language is L1. Because we should remember that for generation of the limit, I can be wrong for as long as I want, as long as I'm eventually right. Right? That's the kind of like relaxing thing about generating the limit. It's fine to be wrong many times. So I'm going to start with the hypothesis that the answer is L1. And as long as the sample is a subset of L1, I just keep outputting strings from L1 minus ST, which again, L1 is infinite, so I can always just find a string that has it. If I ever get to a step where I'm proven wrong, where L1 is no longer consistent with what I've seen, then I move on to L2 and I just keep going. And so you sort of feel like, oh, maybe there's actually just a proof, again, a 1-paragraph proof that this works, because the 1-paragraph proof would look kind of like, well, if I'm currently thinking it's Li. If Li is not right, then eventually the enumeration is going to reveal something that tells me that it's not right, at which point I'll move on from Li to Li plus 1. And the correct language is in this list. It's L sub z, right? It's L sub 100. It's sitting out there. And so if I always move on when I have the wrong hypothesis, I will eventually just crash into LZ. And then I'll never move on because I'm at the right answer and I'll just generate forever. And so it has all the ingredients you want, which is like, I'm going to win without knowing when I've won. I don't know that I've arrived at LZ. It will turn out in retrospect that I never moved on from LZ. Okay. So that's the outline of the wrong proof that, right? It was tempting. You sort of know something's wrong because there's nothing really about generation. Like, we know this doesn't work for identification. What's the problem with it? So the problem with it, as you may have seen already in looking at this proof, before I ever get to LZ, maybe LZ is here, maybe there's some larger language that properly contains it that's earlier in the list. Right? So before I get to LZ, there's Li that properly contains it. The problem is positive examples only. All I ever see is, I never see negative examples. So I'll never move on from L sub I. Because L sub I is bigger and it just traps me. It's like a filter ahead of LZ. And the problem is I'm now going to generate infinitely many wrong things because I have too big a language. I mean, maybe L3 is like all strings, for example. Then we're going to move on from the set of all strings. Okay. So right. And somehow we can't just like somehow wish this problem away. Like it's not like think about it slightly differently, we get around this, because otherwise we'd solve identification limit, right? This would have been a nice strategy for identification limit. And in fact, it is Angluin's algorithm for finite collections. Because if I had a finite collection of languages, what I could do is I could take all the languages, look at the partial order under set inclusion, and I could topologically sort it so that subsets always come before supersets. And if subsets always come before supersets, this problem won't happen, and that will actually be a valid algorithm.
It also works whenever no language contains another.
Yes. So there's a bunch of, which is also right, part of her, part of her condition, right? Her condition ultimately is that there's basically, each language has like a finite set that, is not contained in there. Yes, exactly. So that's sort of key to her characterization, is getting this algorithm to work, basically. Like, when does this algorithm work? We want to go beyond this algorithm because we want something that works always. So we have to work even when, and of course, with a fully general family of languages, I could have an infinite descending chain of subsets, right? Where like L1 contains L2, which contains L3, which contains L4, so that there would never be a way to reorder them to have this nice property. I'm going to have to deal with infinite descending chains of languages. Okay, so what to do? Well, just to kind of draw this picture a little more nicely, right? The languages we can think of as like these bit vectors, right? So L1 contains string 1, 3, 5, 7, whatever that is, 11, 12, and then L2, and then here's L3, which contains everything. Maybe L5 is the right answer. And then the adversary enumerates some things, right? So U12, they enumerate U12, and actually everything in our first step is consistent with that. This goes on forever. And then they output U9, that wipes out L1. Everything else okay, and so forth. Now, I guess the problem we face is that, right, we would like to do something like the algorithm on the previous slide. We'd like to move down the set of hypotheses. And obviously the problem we face is we get to some place and we're like, okay, this seems pretty good. I'll just stay here, right? Everything I've seen is consistent. But you can't stay here because you might have stopped too early. So, but if you can't stay there, it means you're going to have to move on even when everything looks right. If you move on when everything looks right, you're going to move on once you're at the true language. And now you're just going to be drifting out to the right forever with nothing to stop you. But like, whatever stops you, you're beyond. The only thing we had in that argument was that you'll stop at the correct language. Once I'm beyond that, what am I doing exactly? Okay, so we've covered this ground. Obviously, it's useful to look for like minimal languages, but we might not have minimal language. We might have some infinite descending chain of languages. All natural numbers greater than 5, greater than 6, greater than 7. It just descends forever. So I can't quite do that. So you try things out and then you sort of stumble over a definition that's incredibly useful. And once you have this definition, everything actually starts to work. What is that definition? I want things that are minimal, but only if I look back to the left. Okay, so what I'd like is languages that are sort of thin in the sense that they're consistent and they're subsets of everything consistent to their left. To their right, there might be things that are even thinner than they are. But these are all infinite sets, so I'll use thin as my comparative adjective. But there might be things thinner than they are out to the right. But to the left, it's as thin as possible. I guess that's the definition. L sub n, language L sub n, someone on this list, is critical at step t. If one, it's consistent at step t. And second, any earlier consistent language is a superset. That's going to be the definition. So here are two things about this. One, at every step t, there's at least one critical language. Like the lowest indexed consistent language is critical because nothing consistent before it. So just by default, it satisfies this vacuous. And second, the true language might not be critical for a while. There might be a while it's not critical, but it will eventually become critical. There is some step t plus, so that for all t greater than or equal to t plus, L sub z is critical at step t. And this has a short proof, right? Like if you think about it, like this example, L5 is not critical right now. It's not a subset of L4, and L4 is consistent. But we know that can't last forever because L5 contains the string, and eventually that string is going to get output. So in particular, right, take any L sub I that LZ is not a subset of. Well, there's some string that's in LZ but not in LI. And actually, the one and only time when I use the fact that the adversary has to enumerate the whole language, the adversary has to enumerate that string at some point. And therefore, that's going to rule out LI. And then all that we left, looking back to the beginning of the list, are things that are supersets of it. Right? Anything that's left that's consistent will be a superset of LZ. Because for everything that's not a subset of, it's been ruled out by something. All right, so it'll eventually become good. And with that, I can give you the algorithm that generates in the limit, which is the following. in step T, we're going to look at the languages L1 to L2. So we're going to look at wider and wider finite windows. Find the highest indexed critical language among L1 to L2. And just generate a string from L and T. That's the algorithm. Look for the rightmost critical language among the first T languages. Good. So why does this work? Again, once we have the definition of critical, the proof is not long. Let's go out far enough to some time T star that two things are true. One, we're beyond time T plus, so the language is critical. And two, the true language is in our window, right? We're going to look at L1 to LT, and T star is bigger than Z. So Z, the index of the correct language, is in that. Okay. That means from step T star onward, the rightmost critical language lies to the right of LZ. And it's critical. So it's a subset of everything to its left, including it's a subset of LZ. And if it's a subset of LZ, then anything you generate from LNT is going to be generated from LZ. Right? Once you've localized on a subset, you can just generate from there forever because. Okay. And so that's what the algorithm looks like. And so in a way, and this is what I'll try to get to in the next few slides, what's interesting is not just, okay, so we can do it, but the structure of the algorithm, right? The algorithm is basically finding this, it's sort of proactively finding this infinite descending chain of languages, these critical languages, right? They go out to the right, they get thinner and thinner. Each one is a subset of all the ones that came before. And we're not sure where LZ is in that list. I mean, first of all, the set of critical languages is dynamic, it's evolving, right? Because as stuff gets ruled out, they drop off the list of critical languages. So list of critical languages is not some static object I append to, but it's actually something that's kind of churning. But LZ is always in that list, okay? And then beyond it, there's some turbulence. Languages come, languages go, but it's always this infinite descending chain. I keep moving to the right. And I'm never sure, I don't know when I've passed LZ. Like I might not yet have passed LZ. Maybe LZ is still to my right and I'm still hallucinating. But I will eventually, at some moment I don't know, pass LZ. And because of course I don't know when to stop, I'll just keep going forever to the right. But beyond some finite time, I'm into this region of critical sets which are all subsets of LZ and it's always safe to generate. That's the sense in which I kind of alluded kind of vaguely at the beginning to, we're going to do a kind of controlled type of mode collapse, right? Because we're just going to keep shrinking our language and we know eventually we'll have shrunk it enough. All right. So the structure of the algorithm is actually ultimately maybe more interesting than the fact of this result itself. And it kind of invites us to think a little more about like what this means. So let me do a few different extensions from here of this basic fact. First extension, I say final issue, actually it's the first of maybe 4 final issues. So one, recognizing if a language is critical does require answering subset queries, which is not something I can do with an algorithm that only has access to this black box membership. So far I've been in the sort of aesthetic of the Gold and Angluin results, which never worried about computation, just worried about this back and forth game. On the other hand, like, that was fine for negative results. Like, it's fine if you prove a negative result that it's negative, even if you have an oracle. But if you're proving a positive result, it'd be nice to have an actual algorithm. So let's have an actual algorithm. I'm not going to go into details of this just because it gets a little messier, but we basically have to like tear down our definition of critical and do something that involves only finite number queries. So what we're going to do is, as we move to the right, where we widen our window, in step T, we're going to consider languages L1 to LT. We're also going to move, we're going to also consider longer and longer prefixes of the languages, right? We're going to work with finite prefixes. And this is sort of a standard trick you might do. So Li of M is just the prefix on the first M things. And we're going to say Ln is now T comma M critical if it's consistent with ST. And also it's a subset of anything earlier that's consistent on the prefix of the first M elements. Okay. And so what we'll do is say, again, this is sort of a sketch, we're going to consider the first T languages. We're going to try to generate from the rightmost TM critical language. And we're going to maintain a prefix that's growing. Okay, so what we're going to do is generate a string from LNT that hasn't been seen before. Now to do that, I'm like, okay, I'm here, I'm looking for a new string. So I'm going to start walking up this list looking for a new string. And as I do that, I'm going to increase M sub T. And so M sub T is going to increase basically to where I found that string. Now, as I do that, the identity of what's critical can change because I'm learning new things as I go. But the point is, beyond some finite time, the true language will always be T m critical for all m. So basically, once I'm beyond the true language, I'm walking up here looking for strings, changing my definition of what's critical. But I know I'm never going to move left of this thing, because this thing is always critical. Okay, and so I'll eventually find something from a critical language. Right, worst case, I fall all the way back to here, but that's actually good news for me because I'm happy to be in this language. Okay, and that's basically how the algorithm works as an algorithm. I work on prefixes, I climb up looking for strings, I update my definition of critical as I go. But I know that eventually, beyond time t plus, I'm always, I always have the correct language, the true language. Okay, that was a first point. Second point, let me mention the finite, the case of finite questions. Yeah.
So is it maybe accurate to say that this algorithm is like proving a version of Gold's theorem where instead of having to identify the actual language after some time step, you just have to identify some index that's a subset of
Subset, that's the whole game, yeah. Right. And strictly speaking, generation, I'll come back to this question, like, right, so you could say,
difference, right?
sorry,
That's kind of like the difference between identification.
totally difference. That is the difference, yeah. Let's say that's a sufficient way to generate a limit. An interesting question I don't fully know an answer to, or even, I'm not quite sure what the correct formalization of this question is. Are those two problems equivalent? One is find subset, one is element-wise generate. Because right, this is in a sense doing something stronger, which is, no one said you had to guess an index. You could just output strings, but it did guess an index. Yeah.
We already stopped. Like, one of the things that you see here is that kind of you can converge on a subset that's like smaller and smaller. Can you maybe characterize when at least the subset you converge on contains like a positive density of the original set or something?
Yes, and that's the part I'll get to. Yeah, that's more recent. So as of this, we couldn't. And then this new work with Bon Wei that we've been doing is getting at exactly this question about positive density. Yeah, so I'll say a little about that. Great. Yeah, no, thanks. That's I won't get to that in a couple slides. Because yeah, that's sort of where this starts to get even more interesting, sort of this quantitative question. Yeah, the subset, this is where, I mean, just we were sort of fascinated by the fact that in these 60 years since Gold's theorem changing to subset, like I guess we went back to the original people and asked, like, can we, and this does not seem to be a question people were asking for whatever reason. Okay, so the finite case is very different. So let me just digress. This is actually off the critical path because the proof for this is totally different. It's very short and it uses the closure. Okay, so I want to say this proof is probably has sort of nothing to do with the first theorem. I want to look at a finite collection and give you a priori finite bound after which I will generate correctly. And again, remember the closure is just sort of this convex hull-like object. It's the intersection of all consistent continuity. Okay, so proof sketch. Here we go. Actually, this is just the proof. I have a finite collection. Okay. Observation one, if the intersection of all the languages in the collection is infinite, you can just generate from that collection forever. So then I actually don't even need data. I just did. So otherwise, let's assume the n-way intersection of all of them is finite. Now, of course, the one-way intersections, you know, each language by itself, those are infinite. So I have this set system, right, where the n-way intersection is finite, the singletons all have infinite cardinality. So consider all the sub-collections that have finite intersection. Right? That's like an upward closed set system. Okay. So consider all of those sub-collections finite intersection. Each of them has some size, and there are a finite number of those. So let's say m star is the maximum cardinality of any of these intersections. Okay, so what do? I just ask for m star plus 1 strings. Right? So it produces m star plus 1 distinct strings. Now the point is, consider the closure. Consider the intersection of all those. Well, it has cardinality m star plus 1, so it must be infinite because the largest finite collection was m star. And so once I have these, I just go through and I find things that are consistent with all the languages that this is contained in and generate a new string from that. Okay. And so that's the entire proof. This actually, subsequent to our work, Lee, Raman, and Tiwari wrote a follow-up paper. I'll mention a couple other follow-up papers later on, where they actually were asking, like, you could try to run this argument for infinite collections, provided you have this m star, right? And so they talked about the notion of like a collection having what they call finite closure dimension, just meaning that for every subfamily, either the intersection is at most n star or it's infinite, right? And if you get that gap, then you can, sorry. And that gives you sort of generation with this a priori bound from working. It also gives you this sort of, this combinatorial quantity that's kind of interesting to ask about, like, you know, if this were the set of all k-state finite automata, then the bound that we're talking about is large, right? It's basically saying, what is the largest finite set I can produce by intersecting an arbitrary collection of these automata? And it's an interesting question, like, can you do quantitatively better? Like, is this large number somehow necessary, or can you get smaller numbers and get the same kind of guarantee? I don't really know.
How
Yeah.
bad can it be? Like, if you have N languages, how bad can this thing be?
I actually don't have a good upper, I don't have a particularly interesting upper bound. And if I move to like finite tree languages where intersection problems become undecidable, you actually get to even more interesting, intriguing questions, like how big can this intersection be? Like it appears it could grow super fast. For finite automata, I think it grows like some nested exponential, but I don't actually have a particularly interesting bound to say there. Yeah, it's a good question. Okay. Back to the finite case, let's go back to the density question, because that was the thing that fascinated us really was I'm moving out to the right through thinner and thinner languages, and it felt like clearly our algorithm can basically go, okay, so first of all, yes, this is your alternative definition. The current algorithm can produce, so let's stick with the definition where we're guessing languages and looking at their density in the true language. I could do other things, but let's do this one. So certainly the current algorithm can produce things whose upper density in K converges to 0. That's definitely clear. And so the question is like, must every solution to the generation limit have this property? Which initially I thought, I guess my original intuition was like, yes, this algorithm somehow feels inevitable, because after all, you have no idea where the true language K is. I just don't know. And so I'm just, what choice do I have but to keep going forever? I'm just gonna go through thinner and thinner things, but I can't stop because maybe I'm not even yet at the true language. So it felt like the answer was yes, and this would be kind of an intriguing theorem to prove. Like, this is kind of like the hard compromise you're making. Yes, you can generate the limit, but you must do it from the 0 breadth. And wouldn't that be an interesting, like, inherent limitation of generation? That turned out, and there were some partial results that said, like by Charkar and Paroj, these are two papers that built on this thing we were doing. This was at Stock, actually at Stock this year, coming up, saying like, well, you can't generate everything. Like, you can't have density 1, basically, is what this was saying. But how about positive density? Like, what, something? So, okay, and so it turned out what's going on here, there's more that you can say. And in particular, a first theorem that we can prove is that there's actually an algorithm that achieves index-based generation limit, which gets the correct language infinitely often, which is something I did not think a priori you could do. But once you realize it's possible, the trick to do it is sort of natural. So let me tell you how this algorithm works, right? So the goal is guess the correct thing infinitely often. Obviously, you can't guess it forever correctly, because that would be identification limit. We know you can't do that. But so obviously what this means is you're going down this list of critical languages to the right. But if you want to achieve this guarantee, you also have to move back to the left sometimes. Now, the problem with moving back to the left on the set of critical languages to get to bigger and bigger languages is that there's the risk I overshoot, that I get too enthusiastic and I go to the left of the true language, and now I'm generating wrong things. And if I do that infinitely often, I don't generate the limit. So I have to come back to the left in a controlled way, so I never accidentally overshoot. But I come back exactly to here. Right? I have to come back exactly to here. Right? And initially I was like, I didn't see how to do that, but it turns out there's a way to do this, which is not that hard in retrospect. Here's what you do. The adversary is enumerating strings in the language. And there are two cases. Either the string it's enumerating belongs to all strictly critical languages that you're currently considering. In which case, just do what we did before. Just have this wider and wider window, keep going to the right. Because again, I don't have to do this infinitely often, so I'll concede those steps. Otherwise, there's some critical language out here that the string does not belong to, and they're nested, so it doesn't belong to any of the ones beyond that. Right, so picture the critical languages are like this long thread, right? This long thread of beads. And either the string is in all of them, or it's only in a finite prefix of them. And then we snip the thread. Now, as soon as we snip the thread, new critical languages appear, because the definition still applies. Right? So the thread gets snipped, and a new thread emerges with different critical languages. Every time the thread gets snipped, drop back to the language, the bead, just where the thread got cut off. Okay? And guess that one. That's the alpha. Now, the point is, let's think about like L7 is currently here. L7 is a proper subset of, oh yeah, also let's change definition of critical to mean like it's a proper subset of all of the ones. So we don't have this K twice or something. L7 is a proper subset of K. So there's something here that K has that this doesn't. And at some point that will get enumerated. And the thread will get snipped. Now the thread gets snipped actually, in the meantime, something in between might have become critical. So that's a problem. But there's a finite number of things here. So I can't have a chain that descends infinitely. There will come some moment when I can't descend infinitely, the thread will get snipped and I'll move back to the right. At that moment, K is the last critical language that survived. And I'll guess that. And that has to happen infinitely often because wherever I am, look at the next critical language. There can be a descending chain back from that that's finite. And so I'll infinitely often guess the correct language. So it turns out I can actually like hover right at the exact boundary where I want to. And that was a surprise to me, right? Once you realize this, it's not that hard to do. But so what that means actually, that's just a more careful version. Couple of things to know. First of all, we can't do this forever. And in fact, we can't even avoid zero density. So there exist instances where any algorithm chain generation limit must infinitely often produce a guess that has zero density in K. Simple examples, like here's a simple example. Consider the languages where L0 is all finite length sequences of natural numbers. That's a countable set. And Ln is a set of all length n sequences of natural numbers, which is a subset. So what the algorithm can do, so let's say the true language is going to be L0, all finite length sequences. The adversary is going to enumerate, first it's going to enumerate from L1 for a very long time, which means if you're going to generate the limit, you have to guess L1 something. Then it expands out to L2. It's going to generate from L2 for a very long time. Now you have to guess L1 or L2. Then it expands out to L3. At some point, you'll have to eventually guess L1, L2, or L3. All of these have zero density in L0, so infinitely often you regenerate. But the point is, using this algorithm, you can also, in between, intersperse that with correct guesses. Right, so there really is inherently in generation, it turns out, this oscillation, if you're doing it as well as possible, between being right and having zero density, right? And you actually end up having to sort of jump back and forth between them. Okay. So in other words, when I think about the upper densities of the languages I'm guessing, right, this algorithm is going to have the property that the lim_inf is 0 and the lim_sup is 1, and there's no way to close that gap, right? Like you can achieve lim_sup of 1, but you're always going to have lim_inf of 0. And the original algorithm we had just had limit of 0. Like our original algorithm had instances where it just converged to 0. Right? This one maintains that gap forever. So there's more stuff that Fawn and I have been doing with this, but this is sort of like a sort of tip, sort of the beginnings of what's possible. And it's based on the fact that you can actually do more. It was sort of appealing in a way to think that like the algorithm we had was just kind of like that was it, but it really wasn't. Other things, just to start wrapping up. Everything I've said here, one last digression before we conclude. Everything I've said here has been about just generating strings. I said the goal is you see some strings and you have to output some strings, right? You see C programs pass in front of you, you have to output valid C programs. Of course, you might say, wait, that's not how I use large language models. I give it a prompt. I don't say just say something. I say complete my, here's like the beginning of my C program, please finish it for me. It turns out everything we've done just carries over directly to prompted generation. So let's imagine what we're doing is saying in every step, so what's prompted generation? It's the way we actually use LLMs. In every step, the adversary provides a new string from K, that's the training data, and a prompt, that's the challenge to it. And the adversary must output a valid completion C sub t so that the prompt concatenated with the completion is a new string. So you say something, I say something. And actually, if there are only a finite number of valid completions, things get messy. So let's make our life slightly easy with an assumption, which is, let's imagine the adversary provides what I'll call a robust prompt, which has arbitrarily long valid completions. Okay. So they're like arbitrarily long ways to successfully complete this. Okay. The new string and the prompt are really just two parallel activities that are going on, right? Namely, the algorithm is getting new training data. Meanwhile, users are giving it new prompts. These are just two different things going on, but we'll just kind of interleave them together because the goal is to just eventually have enough data that we can succeed. And then actually the basically the algorithm as is achieves prompted generation limit. Like if you think about our algorithm, which says go for the rightmost critical set and then begin looking for a string, the algorithm is identical. It just says now look for a string that begins with the prompt. because since we made this assumption that makes our life easy, you will eventually find one. Okay. There are actually a few results you can do, even if they have only a finite number of valid completions, it gets messier. Okay. And with that, let me actually wrap up. We're trying to wrap up at 11:30 minutes in. All right. So what's the point here? So generation and identification turn out to be very different problems, right? They syntactically look very similar because, as you observed, it's really about, am I trying to find a subset of language or actually find the language? And find a subset obviously has to be easier, but in fact, it's much easier. Right? And somehow the algorithm that does this is producing these sort of increasingly thin candidates, right? It sort of starts with hallucination. At some moment, it actually has the solution. It has the true language. It just doesn't know it and can't know it. And it keeps going on toward this kind of mode collapse. And even with the stronger algorithm I was telling you about at the end, it kind of oscillates. So it sometimes backs up the solution, but it can't avoid kind of also having this interleaved kind of mode collapse. It's sort of interesting. Like once I thought about the structure of these solutions, a colleague of mine, Cristian Niculescu Mizel at Cornell, who works on kind of empirical studies of online social media, who I've worked with in the past on very different topics. There's sort of an interesting parallel between what this algorithm was doing and some studies he did 10 years ago on how people acquire the vernacular in a new community, right? So like you start contributing to a new subreddit and you show up in the subreddit and you discover like people have certain idioms, they have certain ways of talking, certain slang, you don't really get it. And so you sound like a newcomer because you don't know how to use the slang. And as time goes on, you figure out the slang and you use it and you actually sound like you belong there. You actually use the idioms. But as you continue to stay there, you age, and this is actually what he found in the data. He has these beautiful plots of how this happens. As you age in the subreddit the way people age in real life, which is you don't pick up the new idioms that the young people are using. You keep using the old idioms that were there when you first arrived. And so you sort of linguistically age out of the community. You just don't pick up the new ways of talking. And what's sort of interesting is like our algorithm is, for totally different reasons, kind of doing this. It starts out babbling and saying way too much. It says invalid strings. There's a moment when it actually has it right. It's figured it out, but it doesn't know that this is right. And so it keeps going and keeps being more and more rigid in what it's willing to say. And in the process sort of has this kind of like mode collapse. Again, for different reasons. This is, in our case, it's about the hardness of identification. In this case, it's just about you can't keep up with the language as it literally evolves, right? Our language is not really evolving. So I feel like it's for different reasons, but there's something intriguing about this kind of like collapse that's happening in both cases. And so again, this question that's motivated a bunch of the recent work, which we now have some partial understanding of, is must every solution to generation limit have some kind of structure? Not exactly. We can do better than the original algorithm, but there is always going to be some kind of inevitable mode collapse that's going on for certain instances. And so a number of follow-up papers that have been going on. I think there's a lot of interesting questions still remaining here, and I think that's beginning to give us some insight into how to formalize things that have just been thus far very hard to formalize in the space of large language models, to really talk about the breadth at which they can generate, the richness of what they can generate, and the trade-offs with the kind of correctness guarantees that they have. So I'll stop there. Thanks very much.
So, any questions or comments?
Yeah.
What means in your theorem 2? Theorem 2.
Yeah.
How to relate to the hallucination of Adam Clay's results?
Oh yeah, right. Adam Clay's results on hallucination. Yeah. Yeah. So right. So Adam Kalai and Sandra Frontala, if these are the ones you think about, had these results on hallucination being inevitable. And the idea was that if I'm going to generate from the language with any kind of richness, any kind of breadth, I'm going to have to say incorrect things. And the argument roughly, so one big difference is that their arguments are all probabilistic in nature. So they say basically, consider any distribution on strings, and now consider a finite sample drawn from that distribution. They're going to have to be a bunch of strings that occurred once, and then a bunch of strings that are valid that have occurred 0 times. And if I'm going to generate new things, I sort of have to generate from things that occurred 0 times. And I can sort of figure out the rate at which I'm doing that. And some of those won't actually be valid, and those will be hallucinations, right? Right. This sort of, I mean, Adam relates this back to the good Turing estimate.
Yeah. Exactly.
Right, exactly. And that sort of, I mean, as Adam describes, he sort of says his paper can be summarized in kind of one sentence as like, this is applying the good Turing estimate to large language models, that you know, like Turing, anecdotally, the story goes, was using this to try to figure out the sort of, you know, rare code words in the Enigma cipher, right? You'd see rare ciphertext that occurred once, and you try to estimate how many messages you hadn't seen. Like how many unseen things are there from the number of things you've seen one time. And if you make certain assumptions on the distribution at which you're sampling the training data. And so that's kind of what Adam is doing. And so it's really exploiting this kind of like estimate you get for sort of generic sampling from a large set. This is somehow saying something about worst case, right? The adversary is literally doing it however they want. And despite that, we're able to say something. So it'd be interesting to ask a question about hallucination. I mean, clearly in the worst case, you're certainly hallucinating. The adversary can certainly make you hallucinate. But trying to bound how much, this is sort of saying this is a maximum amount of hallucination in the finite case. Again, in Adam's case, the set of possible languages is infinite, so we're sort of more closer to theorem 1, where you could, you know, it's a good question though to try to figure out exactly how they like Adam is concerned with breadth, and one way we're getting right. So Adam says you can hallucinate forever because you want sufficient breadth. We're willing to sacrifice breadth. We're willing to look at an arbitrarily small, thin finite subset of this, but we want to make only finite many hallucinations. So maybe that's part of the contrast also. I will say one thing that starts to try bridging these. So this paper coming up in Stock by Kalavasas, Mirocha, and Velakis is looking at a distributional model of this, which is saying, imagine that the adversary thinks of a language, so L1, L2, L3, countable set of candidate languages, true language K, the adversary commits to K, and not to an enumeration of it, but to a distribution over K. And now after that, it's out of their hands, they're going to IID sample from that. That makes the problem more tractable, because once you commit to a distribution, like it's going to have to sort of be numbers that no matter what oscillations they have are sort of in the limit descending. And so there's a certain like ordering on the strings, and certain strings are going to be much more abundant. So you get more mileage out of this once you make a distribution. Language identification also gets more tractable there. To come back to like tractable case of identification, if I say now I'm committing to an ID distribution over strings, I can say certain things I can't. So this might be some way to also bridge partially with Adam's result.
Wondered about you started with this hourglass.
Oh, yeah.
before, and you said something about the interface between how you build the LLMs and how you use them.
Yeah.
So can you kind of, now that we've heard the talk, can you say?
Come back to the hourglass picture. So I sort of want to think of this two-party interaction. Nature generates strings, the algorithm tries to produce new strings. We have this generation limit guarantee as a kind of like one notional kind of thin part of the hourglass. Because what it allows us to do is sort of put our finger on this notion of breadth. And I think this notion of density is actually very useful for thinking about this. Like, which is interesting because of course the combinatorics of like densities and like countable sets of natural numbers is always often gets very rich. Yeah, so I think like this idea of the two-player game you must generate, and now we're asking about the breadth at which you generate, is a kind of like a very simple abstraction of a gigantic lower lobe of the hourglass that has like the transformer architecture, the 100 billion parameters, the training data. But like ultimately you're trying to generate new strings at a certain breadth. And so here's a question that I feel like we could ask, at least ask, which had never occurred to me to ask until we had this model, which is take ChatGPT, take Claude, take Gemini, right? You prompt it. Ask yourself, what fraction of the English language can you get it to say with a suitable prompt? Right? Can you get now? And let's say with a short prompt. So I could always say like, say the following quote, and then put whatever string you want, and I guess it'll probably output that back. But like, let's say with with short prompts, with some family of prompts that we decide is a reasonable set of prompts. Could I say, for example, that one of those three LLMs is actually more expressive than the others? Right? That this one can generate 0.5% of the English language, and this one can only generate 0.01% of the English language. Right? Is that like, it's a well-defined question. As in, you can either get it to say this thing or not with a short prompt. And it's not clear. And so I feel like because of this, we can actually now start to ask them these questions.
Fine. I mean, what is the English language that you're generating? True.
It's not clear it's totally well-defined, right? Again, when I'm off that and fully well-defined, I fall back on like C programs. Like what fraction of all C programs can you get it to say? Because it is well-defined, like what's a C program?
What's a valid C program?
Yeah, because it either passes the compiler check or it doesn't. English, it's a little harder.
No, but even there, you feel like there should be some distribution over.
Maybe, yeah. But these are exactly the questions I think are good to ask. Like, we want to ask the question, like, you sort of feel, I mean, people talk about like, this LLM, I feel like is just more expressive than this one. This one has a much more constrained way of talking. We really have very little way to empirically like measure, like, let's put some measure on that. And if it has to be a heuristic measure, that's fine, but it's formulating something that feels real to us, which is like, people feel like, Claude really feels more expressive than ChatGPT, for example, and so it uses richer language. So is there a way to actually formalize it? We've been thinking about this with image generation also. So like a paper we just, Sentinel and I with Sarah Bentley and Kian Vafa just put on arXiv was about steerability of these models. So like I have a certain thing that I want it to say. I want to prompt it. Like an example, like text, you can do this, but like image generation, it's very clear. I have a picture, so like this picture is AI generated. I said, draw me a set of printouts of C programs sitting on a table, right? And so actually, if you look close, it's not even writing words. It's actually kind of creepy what it looks like. But anyway, it's just a set of printouts of C programs sitting on a table. Right? And I was fine with this one, but of course I had in my head a picture, right? So when you ask it for clip art for your talk, you're like, draw me a self-driving car going up a hill, right? You have a picture in your head, and it draws it, and it's not what you wanted. Like, no, make the car more high-tech, make the hill steeper, make the weather more cloudy and threatening, right? Like, have there be a car coming the other way. So you keep trying to get it to the thing you want that's in your head, but there's a communication bottleneck because it's in my head very vividly, but I don't draw very well. I can't like draw. I mean, if I drew very well, I wouldn't be doing this in the first place, right? So how do I like steer it to the, and is prompting even the right way to do this? So that's also a kind of like expressive. So there's two things going there. One is there any way to, like an existence question? Is there a short prompt? And so we did these experiments where we produce a picture with a short prompt, and then we challenge people, say in Mechanical Turk, whatever, produce this picture. I promise you there's a 15-word prompt that does this because I produce it. Very hard for them to find this, right? It almost feels like this weird like cryptographic search for like, that's like the 15-word key. And you try and you just orbit around this picture and you can't seem to get it. So there's the existence question, then there's the steerability question. And the two are different. And so I think that also is sort of gets at this question of breadth, which all these are things that we sort of hope to be able to start.
And you were extension to the adversary produce noise example. Can we use Drew Footman's new concept, single to loss ratio, and connect with Adam Clay's hallucination rate?
Interesting. I see. So we have two things like hallucination rate versus signal, and try to say this is what's being traded off.
But I did not see your paper.
Yeah,
it's good. I only see the old version.
Yeah, it's a good question, which that may be a way to relate to Adams. Yeah.
Yes, I can discuss with the football.
Sounds good. Yeah.
Okay.
Thanks.
Any more questions or comments before we head to lunch?
Very great.
All right. Thanks.